In this video, we're going to talk about the kernel and the range of linear transformations. So now that we've talked about the null space and the column space and how they relate to matrices, we can generalize them to talking about linear transformations. And when we talk about a linear transformation, we usually don't call the null space and the column space the null space and the column space. We have different words to refer to them. And those are the kernel and the range. Okay, so I want to begin with the definition of what a linear transformation is, but when we talk about vector spaces, and not just Rn and Rn. So what this definition basically says is, if you have a transformation T, where you input things in some vector space V, so that's the domain V, and the codomain, the set of possible outputs, is some other vector space W, so T is still going to be a function. And what makes it linear is it satisfies these two properties that we know linear transformation should. So T of U plus V should be equal to T of U plus T of V, and T of C times U should be equal to C of T times U. For any vectors U and V that are in the vector space V, so in the domain, and any real number C, so any scalar C. Okay, so the kernel of the transformation is the set of vectors x that are in the domain, in V, in the vector space V, such that T of x equals 0. So the kernel is the analog of the null space. This is the analog of the null space. That's what the kernel is. And I'll draw a picture of my domain and my codomain to help us visualize this a little bit in just a few seconds. But the range, so the range of a transformation we've actually seen before. Conceptually, the range is all of the outputs we actually achieve. So in set notation, the way I write that is, it's the set of T of x. So T of x is representing an output after I plug x in. And that's why it says it's in W, such that x, let me put a vector on that, x is in V. So x is in my vector space V. And the range is the analog of the column space. In fact, in the last video, when we talked about the column space, one of the things that we noted about it was the column space was the same as the range of a transformation. Okay, so let's draw a picture. Let us draw a picture. So let's say that we have a circle that represents my domain, which is some vector space V. And let's say I have this circle that represents my codomain, which is W. So in terms of my picture, W, so both of these things are vector spaces. But W, let's just say I focus in on the zero vector of W. So the kernel is all of the things in V. So all of the things that are in V, let me just draw a circle to represent them, that when I plug them into my transformation, when I plug them into T, I will get out the zero vector. So all of these things in this blue circle that's in V get mapped to just the zero vector. So even something here gets mapped to the zero vector. If there's something else in the kernel, that also gets mapped to the zero vector. But that's what the kernel is. Everything that's in the kernel gets mapped to the zero vector. The range corresponds to the outputs that I get when I plug in everything that's in V. So when I plug in everything that's in V into T, I'll get out some of the things that are in W. Maybe I'll get out something like this. Maybe my range. So I know 0 for sure is going to be in the range. I can always get out 0 by plugging in 0. But the range might look something like this. So notice that I'm deliberately not drawing it as big as all of W, because I don't necessarily know that the range is going to be all of W. If it was, my transformation would be onto. But the range is this gray area that I've just drawn in. But notice that the range lives inside of W. The kernel lives inside of V, inside of my domain. So next we are ready to state a theorem about the kernel and about the range. Okay, so the theorem is, I think, kind of what we'd expect. It's an analog of something for the null space and the column space. So the first part of it says that the kernel of T is a subspace of V. Like we noticed in the picture, the kernel lives inside of V, inside of my domain. So the proof of this is really similar to the proof that we gave that the null space is a subspace of Rn. So I won't give a proof for part 1. I will give a proof for part 2, however, though. So part 2 is that the range of my transformation is a subspace of W. And like we just saw in that previous picture, the range lives inside of W. And now we'll be showing, oh, not only does it live in W, it is a subspace of W. Okay, so let's prove 2. So if I want to prove something is a subspace, I have to show that it satisfies those 3 conditions that a subspace should. So the first is about the 0 vector. So is the 0 vector, so when I talk about the 0 vector, so is the 0 vector in my set? In this case, my set is the range. And when I'm talking about the 0 vector, because there's 2 vector spaces, V and W, I should specify which one I'm talking about, the 0 vector of. So when I'm talking about the range, I'm talking about outputs. So I'm talking about the 0 vector in W. Is 0 sub W in the range? Is the 0 vector of W in the range of T? And the answer to that is yes. Definitely it is, because there's something I could plug into my transformation to get out the 0 vector of W. What would I plug into my transformation to get out the 0 vector of W? Well, I would plug in the 0 vector. But I would plug in the 0 vector of V, because my domain is vectors in V. So that's what 0 sub V means, the 0 vector of V. So this implies that, let's switch it back to black, that the 0 vector of W is in the range. Okay, so that checks off this first property for us. First property is satisfied. At this point, for property 2, I want you guys to think about, well, what's the question I would ask myself here? Kind of like I asked myself this question about the 0 vector. How would I phrase that for property 2? I want to give you guys about a minute to think about that. If you guys get done phrasing it, then start to work on the proof of part 2. So 4, 3, 2, 1, pause the video. Pause the video and think about this for about a minute. How would we phrase property 2 here, the thing that I need to check? Okay, so hopefully you guys have done that. Hopefully you guys pause the video for about a minute. I know it's just been a couple of seconds for me. Okay, so how would we phrase this? This is the statement about vector addition and closure under vector addition. Well, I would need to ask myself, like, if I have 2 things, in this case we're still talking about vectors, so if x and y are vectors that are in my set, and my set is the range, if I have 2 vectors in the range, then, when I add them, then is their sum x plus y also in the range? Is that in the range of T? That's the question we need to ask ourselves and to verify whether this is true or not. So let's break down what it means when we assume x and y are in the range of T. So when we say that x and y are in the range of T, this means that we can get x and y out of T. So this means that T of some vector, let me just call it u, equals x, and T of some other vector equals y. And let me just call this vector v. So this has got to be true for some vectors u and v that are in, so u and v are in the domain. So the domain is the vector space capital V. Okay, so what I want to see is x plus y in the range of T? In other words, is there something I can plug into T to get out x plus y? And the answer to that is yeah, I would plug in u plus v. So then, let's go ahead and do that. Then, if we take t of u plus v, and we simplify this, so using the fact that t is linear, this is equal to t of u plus t of v. That's because t is linear. And we know what T of u is. T of u is x. And we know what T of e is. T of e is y. So we've just plugged in something into T. We've plugged in u plus v to get out x plus y. So because we were able to get x plus y out, that means x plus y is in the range. So this implies, let me just use my implication arrow. So this implies that x plus y is in the range of my transformation. This is in the range of T. That checks off the second property. Okay, so we have one more property to check off. So this is a closure under scalar multiplication. Okay, so what would that look like? We would say if we have some element in our set. So if x is in the range of T, that's our set, and C is any scalar. If C is just an arbitrary real number, the question I have to ask myself is, well then, is C times x also in the range of T? Is that going to be true? Is this going to be true? So the proof of this is going to be very similar to what we did in part 2. So if x is in the range of T, if x is in my set, well then that means that there's something I could plug into my transformation to get x out. So let's just call that vector u that I plug in to get x out. So this has got to be true for some vector u that's in my domain, the vector space V. So it's really important that I write this, for some vector u that's in my domain, that's in my vector space V. Otherwise, it's unclear what this u is when we write T of u equals x. Okay, so now I want to know if C times x is in the range. So the way I would show that is I need to plug something in to T to get out C times x. And what I'm going to plug in is C times u. Because using the property that T is linear, I can pull the C out in front. This is going to be C times T of u. So we have C times, and we know from above that T of u equals x. So we get C times x. And that's what we wanted to show, because now we know that there's some vector I could plug in to T to get out C times x. That implies that C times x is in the range of T. Okay, so finally we can write our conclusion, which is, at this point we've checked the third property, we've checked all three. Since all three properties hold, that means the range is a subspace of W. Okay, so I'm going to end this video with an example. So what does it look like when I have a transformation from a vector space to a vector space? So this is an example of that. What could it look like? So let's say we have a transformation that goes from P2, remember P2 is the set of polynomials of degree at most 2, so 2R2, so the outputs are going to be vectors in R2. So the way that this transformation is defined is T inputs a polynomial, and what it outputs is a vector with the entries of P of 0 and P of 0. So I want to find polynomials P1 and P2 that span the kernel and describe the range of T. So to get a feel for what this transformation does, I want to do an example. So let's say I have the polynomial P of T, which is equal to 4t squared minus t plus 7. So when I plug these into T of P, into my linear transformation, we will get P of 0 and P of 0 as the two entries. So P of 0 means, well, plug 0 into this. Plug 0 into the polynomial. P of 0 is going to be equal to, I'll get 0 minus 0 plus 7. Well, actually, let's write it like that. I'll get 0 minus 0 plus 7, which is equal to 7. So the first entry is 7, the second entry is 7. So that's what T of this particular polynomial is. When I plug this particular polynomial into my transformation, what I get out is the vector 7, 7. Okay. So let's do this more generally now. So what I'm going to do is, let's take some arbitrary element of P2, of my domain, of this vector space. So what does something in P2 look like? Well, it looks like some scalar a times t squared plus some scalar b times t plus some maybe constant term, where the a, the b, and the c are real numbers. So when that happens, if we were to plug in 0 into the polynomial, what we'd get is we'd get a times 0 squared plus b times 0 plus c, and that just equals c. So only the constant term survives. Okay, so let's go ahead and plug in this general polynomial into our transformation. So when we do that, we get, so the first entry is p of 0, the second entry is p of 0, and now we know what p of 0 is, because we just did it. It's c. So we have c and c as the two entries. So all of the outputs that we're getting when I plug in a polynomial into t look like this. They're all vectors where the first two entries are the same. In fact, I could factor out the c and get c times 1, 1. So these are all of my outputs. All of my outputs look like this. That means the range looks like this, because the range is all the outputs we actually get. So we can actually answer the part about the range first. So the range in this case is all multiples of the vector 1, 1. Or another way to say that is the range is the span of the vector 1, 1. That's another way to say it's all linear combinations of that vector. So visually, my range is a line that goes through the origin in the direction of this vector 1, 1. Okay, so this problem is actually answered. It's easier to answer that part about the range first. Now let's see if we can do the part about kernel. So now let's talk about the kernel. So when we talk about the kernel, what I will do is let's set t of p. So t of p, remember, ended up equaling c when I plugged in this arbitrary polynomial. When I'm talking about the kernel, I want the output to be equal to 0, 0. I want to know what do I plug in, what this p is, to get out 0, 0. So c has to equal this vector 0, 0. So that means c equals 0. And if c equals 0, what does our original polynomial look like? So p of t, that original polynomial, will look like a t squared plus b t. So that means anything that's in the kernel is looking like this. It looks like at squared plus bt. So the question was to find polynomials p1 and p2 that span the kernel. In other words, anything that's in the kernel, in this case the kernel looks like this, should be a linear combination of p1 and p2. So notice that this right here is a linear combination. It's a linear combination because I have a times something plus b times something. It's a linear combination of, what are those two things? Well, one of them is t, the polynomial t, and the other one is t squared. So those are our two polynomials that we take the span of to get the kernel. So I'll let p1 of t equal t, that's one of my polynomials, and the other one, p2 of t, I'll call it t squared. So those are the two polynomials whose span is the kernel. So the kernel in general looks like all polynomials of this form where a and b are any real number. Just conceptually why that's the case, why things of this form are in the kernel, is because if I were to plug in 0 for the t, notice that this just becomes 0. So this first entry here would be 0, the second entry here would be 0. So the outputs are both 0. That's why things that look like this are in the kernel.